Hello, my people. I hope that the summer break that you've gotten thus far has been refreshing. I hope that you are all doing real well, and I hope that you're all raring to go for summer trig. Let's go ahead and get started with a couple of just foundational issues. And the first thing that we need to talk about, of course, is what trig is. And sometimes that's sort of overlooked. It's kind of important to know what it is that we're doing and why. And so here I've, just for the sake of geeking out just a little bit, I have pulled from the Etymology Dictionary Online, or etymonline.com, the etymology of trigonometry. And as you might suspect, trigonometry, basically the word means measurement of triangles. Okay, it comes from trigonon from the Greek, which basically means three, and angles, and then metron being measurement of. That shouldn't really surprise us, but that doesn't really get at what trigonometry is, meaning like why it is important. Okay, and so what we're going to do is we're going to talk for a second about sort of what we've done in math thus far, and sort of the unfortunate byproduct of the way that the math curriculum is structured up to this point sometimes makes it kind of difficult for people to make the transition to trigonometry. Okay. Now in Algebra 1, you learned what is called analytic geometry. Okay. Analytic geometry refers to the practice of taking things that are algebraic, meaning equations, and turning them into pictures, geometry. So it used to be that algebra, things that we did with notation, and geometry, things that we did with shapes, used to be two separate domains. And then when you get to about the 17th century, and René Descartes and Pierre Fermat, what they did is they figured out a way of integrating the both of those. Now what we don't realize is that when we're learning how to graph and we're learning things about the coordinate plane, that actually had to be invented over time. Okay. But we work with the coordinate plane, and we graph and we graph and we graph, and things, we just start to assume that that's the way that the world is structured, that everything moves back and forth and up and down. And, that's just the way things are. Well, not really. Basically, this winds up being a rather arbitrary way of measuring things. And so what I'm trying to tell you is basically up and down and back and forth is really good in for what it actually accomplishes and what it helps us do, but it's rather arbitrary. And the world could just as easily, instead of up and down and back and forth, right, it could actually be measured around and out. Okay? So what we have up here is we have back and forthness, okay, and up and downness. And we just sort of assume that that is the way things go. Okay, this is also what is referred to as rectangular. Rectangular ways of measuring and graphing and talking about space. Down here is the trigonometric, okay, or what you will come to know later as polar, because there's a pole right in the middle, okay, but we'll get to that another time. The fact that things go around, things that are measured around, meaning angles, and things that are measured out, meaning radii, okay, you have now outness and aroundness. So there are now two ways of measuring things. Both are equally valid, both are helpful in different circumstances, but we have to figure out a way for them to talk to each other, to translate from one to another. And that's all trigonometry is. Trigonometry is taking triangles, which of course we're talking about not in terms of their back and forthness and up and downness, but in terms of how they are anchored as representations of angles and radii. We are taking those triangles and we are trying to translate them back into the ratio of sides. And the ratio of those sides, of course, is representative of the rectangular. So trigonometry really can just be considered mathematics of translation. Okay? We are simply translating from this measurement principle of outness and aroundness, outness being your radii, aroundness being your angles, and we are basically translating it into the ratio of sides, up and down, back and forth. And as you might have guessed, to go the other way is where we run into inverse trig. So trig gets us from out and aroundness to back and forthness and up and downness, and inverse trig takes us back, okay? Now, the reason I'm laboring this point is the fact that so many students struggle with trig, not because trig in and of itself is difficult, but they fail to make that, they fail to sort of realize that what it requires is a change in your mode of thinking, okay? And so you can't think about outness and aroundness. You can't think about angles and radii in terms of up and down and back and forth. You have to think of them as a distinct means of measurement, okay? A wholly different schema that then we use trigonometry to translate back into this particular sort of comfort zone way of measuring things. Now, what you'll realize later is that in doing this, we are sort of taking it from something that is unfamiliar to a realm of the familiar. When you get to polar graphing, you're no longer translating it back into your comfort zone. You're actually using outness and aroundness as their own coordinate system, as sort of independent ways of expressing measurement, okay? That, however, is for another time. Now, when we get into trig, there is a little bit of vocabulary, and that vocabulary I am going to ask you to know, okay? I haven't decided whether I'm going to quiz you on your vocabulary. I have done that to students in the past because I find it rather abhorrent that so few students actually have a working mathematics vocabulary. And we'll talk another time about why mathematics vocabulary is important. But for the most part, right now, your main concern is the fact that I speak this language. And if I'm speaking this language, you need to understand what I'm talking about, okay? Obviously, there are some of these things that you know good and well what I'm talking about. When I talk about an angle, I am talking about basically the aroundness measurement between two rays where their initial point meet at what is called a vertex, okay? So basically the angle is your open, your aroundness. How far does it open? And when we talk about that, we have the angle, and that would be the whole thing. The vertex is where those two rays have their initial point. And then we have one ray, which is basically referred to as the initial side. Okay, think of it as a hinge that used to be closed. This one stays still, and the terminal side this other one is swinging open. Okay, the initial side is where the angle starts. The terminal side is where it, wait for it, terminates. Okay, it's almost like they name these things on purpose. It's fantastic. In large part, we're going to be dealing with angles as they are basically anchored inside of the Cartesian plane or the coordinate plane, okay? And this shouldn't be a surprise. Basically, anything that we can do geometrically, just about, we can then sort of import it into the coordinate plane and use the coordinate plane as a means of sort of anchoring it and basically being able to manipulate it and talk about two different angles within the same coordinate plane so that we can relate them like right on top of each other rather than having to do them next to each other or something like that, okay? Now, when you put an angle inside the coordinate plane, you need to remember that the initial side is this positive x-axis. And as angles swing open from this positive x-axis, when you are measuring angles like this, it is called standard position. Now, can you have angles inside the Cartesian plane that don't have the initial side on the positive x-axis? And the answer is yes. But we oftentimes intentionally put the initial side on the positive x-axis because there are just certain computational benefits for that. But when it is in this particular way, the initial side on the positive x-axis and the terminal side swinging one way or another, that is called standard position, okay? And as you should know from the little bit of trigonometry that you have already been exposed to, positive angles are when you are swinging this way, right? Negative angles are when you are swinging this way. Positive angles counterclockwise, negative angles clockwise, okay? Now, there are what are called coterminal angles, okay? So if we actually look up here, this initial side and this terminal side actually represent two different angles. We can call this positive one alpha, and we can call this negative one beta. And those two angles are very different, okay? One of them is positive, and, its absolute value is less than 180. This beta, this negative angle right here, its size is greater than 180, but they have the same initial side, the same terminal side, and therefore they are what is referred to as coterminal angles. And of course, it's not just these two angles that are represented. I mean, you can basically spin it around as many times as you want. As long as you start on the initial side and end on this particular terminal side, there are actually an infinite number of coterminal angles, okay? Now, complementary and supplementary angles, you ought to be very, very familiar with those. Those were introduced to you probably before geometry. But just as by way of reminder, complementary refers to those angles where they add up to 90 degrees or pi over 2, and we'll get to radians here in just a second. Supplementary are the ones that add up to 180 or pi, okay? Now, that's it for vocabulary for now. But let's talk about what this means. Now you probably were told how to number the coordinates and the quadrants within the coordinate plane a long, long time ago. What you may not have recognized at that point is they are numbered that way because that is the order in which a positive angle in initial position opens up, right? You basically, if you're in standard position and your initial side is on the positive x-axis, an angle will open up into this quadrant first, this quadrant second, this quadrant third, and this quadrant fourth. So, if you're ever wondering why they numbered them like that, ta-da, there you go. All right, so that's enough for a lot of the preliminary stuff. Let's start talking about radians, okay? Because before we actually get to the trig, we just have a couple of sort of foundational grounding principles and definitions and ideas and all sorts of fun stuff like that that we need to actually deal with, okay? Now, when we are dealing with a radian, we are dealing with something that is an alternate way of measuring angles. That's it, okay? Just like there are multiple ways of measuring distance, right? You have metric, meters, kilometers, and you have imperial, inches, feet, yards, miles. Basically think of it like that. And of course, if you have something in terms of kilometers, there is a way of converting kilometers to miles. You simply have to know basically the ratio of their relationship in order to make those conversions. And it's the same sort of thing with radians and degrees. Now the thing about radians is oftentimes they get to be confusing because students, while this definition is technically correct, I don't find this definition to actually be really all that helpful, okay? Let's go ahead and read through it real quick. Now, it says 1 radian, okay, is the measure of a central angle that intersects an arc S equal in length to the radius r of the circle. Okay, now all of that is wonderfully fun, okay? And what that means, and this picture is actually not related to this definition, I yanked it off of Google Images, but let's say that this right here is r, okay? This length right here, okay, from here to here is s, okay? Basically, what they're saying is that 1 radian is that angle measurement where this radius can sort of be slapped on the outside of this circle and it will be equal. But to make it really, really clear, let's go ahead and I want to show it to you, okay? So we basically have marked on this particular index card how far 1 radius is, right? So that basically is 1 radius in length, okay? And what we're going to do is if we take this thing, we take this same length and we bend it around the outside of the circle. Do you see how that radius, the same length bent around the outside of the circle, winds up being equal to that arc length, okay? And that's what it's saying right there. Of course, you might be thinking to yourself, whoop-de-doo, like why in the world is this helpful? I am so glad that you asked. Because that is exactly what I want to discuss next. Why in the world do we do this, okay? And here's the thing. Here is another way to think about radians, and I actually think this is a better way to think about radians, but whatever, to each his own. If you find the other way sort of comforting and it's your, it's your binky, it kind of keeps you safe and warm and keeps the monsters away from you, then that's fine. You can go ahead and think about it that way. But for those of you who have always found it rather arbitrary, listen up. Now, when we're talking about a circle, one of the first things that you learned how to calculate was the circumference of the circle, right? Now, the circumference of the circle is 2 pi r, okay? Now, 2 pi r, it seems like a formula, but there's more to it than just a formula, because 2 pi basically tells me, what I need to multiply r by to get that particular arc length. Now, we oftentimes don't think about the circumference as an arc length, but it is. It just happens to be a special name for the arc length that goes all the way around. Okay, just like the diameter is a chord across a circle. It just happens to be the very special chord that cuts through the center of the circle as well, okay? So if we think about circumference as a particular kind of arc length, then basically if we want an arc length that is shorter or longer or basically different than the circumference, we simply need to relate the new arc length. We need to relate the new arc length to what percentage or what sort of proportion, how it's proportional to the circumference. So let's say we wanted an arc length, okay, around half the circle. Well, wouldn't I just take half of this? I would take, 2 pi r over 2, and that would be equal to pi r. Okay, well, what if I wanted an arc length around a quarter of the circle? Okay, and that becomes, 2 pi r over 4, or pi over 2r. Well, what's constant about all of these three is the fact that r is there. The thing that's different is basically this constant that is sitting out in front of r. And what it really represents is basically what fraction of the circle are you dealing with. So think about radians as a way of describing angle measurement as a fraction of a whole revolution. And if we think about it like that, then I don't really care how far 1 radian is, right? The reason that this appears so arbitrary to so many people is that you never see 1 radian, and you almost never see 2 radians or 3 radians or 4 radians. What you see is, you see pi over 2 radians. You see 5 pi over 6 radians. You see, 11 pi over 6 and 4 pi over 3 and stuff like that. And the reason that the definition seems arbitrary is that you start thinking about pi over 2 as, well, that's a quarter of a revolution. Well, yes, pi over 2 is a quarter of a revolution around the circle. And actually, think about it like that. And here's the really neat part about recognizing that radians are merely talking about a fraction, like what fraction of revolution it is around the circle. You start to recognize the fact that radians really aren't a unit in the way that like meters or something else is, okay? Like when you're dealing with like a physics problem and you're dealing with velocity in meters per second, meters and seconds are actual units. Radians as a unit sometimes just sort of disappear into the ether, and you're like, well, I never canceled it out. Where did it go? Well, it didn't really go anywhere because it was never really there. Because radian as a unit is almost like a pseudo unit, okay? It's almost there as a way of just calling it something, but it doesn't have the same status as seconds or meters or whatever, okay? Now, like I said, if this helped you in terms of actually understanding why we use radians because it communicates angle measurement as a fraction or as a percentage of a full revolution, whereas, I mean, if you think about it, that actually is more useful. That actually helps us in a way that 360 degrees in a full revolution really just doesn't. If you think about it, degrees are really, really arbitrary. Radians are actually built into, they're basically describing angle measurement based upon the nature of the circle as such, okay? I hope that that's helpful. I'm going to go ahead and bring this video to an end because it's, getting kind of long. But when in the next video, we're going to do some problems that deal with converting radians to degrees back and forth. And those conversion ratios are really, really predictable and really easy. But we want to go ahead and refresh our memories and do a few of those problems explicitly so that it sort of gets burned into our long-term memory. Okay, so I'll be looking for the second video in this series. Bye.